Let's just wait for a couple of more minutes before we begin. Let's begin. Hello everyone, this is Tanya. I'm one of the TAs assigned to the course Aircraft Design taught by Professor A.K. Ghosh. So we will go over the contents of week 4-5 and solve a few questions. I'm sorry we couldn't have the class last week, I wasn't feeling well. Have you all submitted your assignments? How did it go? Okay, so I'll just go over a few concepts. So can anyone tell me what the benefits of high wing are? We've discussed that it's better in lateral stability. That is one of the reasons. What else? What else could be the benefits of high wing? More empty area on fuselage. How? I mean, even if you have your low wing configuration, the amount of area that is empty will just be shifted upwards. The area remains the same, right? Near to the ground. So it's yes. Okay. So ground clearance. Anything else? Okay. So large ground clearance is one of them. Ground clearance not just for maintenance but also if when the oncoming wind is there or when you're landing, it's beneficial if there is a larger ground clearance. Okay, so another thing is while taking off there is a lesser probability of the wing tips hitting the ground. If it's a lower wing, you will have a shorter or lesser range of angle of attacks with which you can take off. Otherwise your wing tips stand the chance of hitting the ground. Another thing is, yes, fuselage closer to the ground, like he said, it's easier for maintenance. Then, if you have high wings, this I think sir has explained extensively in the lecture, that you can have additional supports like struts that have support near the fuselage for the wing, relieving it of loads that it should otherwise carry if it were any other orientation or any other configuration. Then you have enough clearance for maximum flap deflection. So similar to the condition which says this one, lesser probability for wingtips hitting the ground, you also have a larger area or larger region for maximum flap deflection. Why do we deflect flap during takeoff? To get higher CL. So you can have maximum flap deflection and you can have a larger CL max during takeoff if you have that clearance. Okay, so these are the some of the benefits of hiving. I just thought we should go over this before we get into the questions of week 4, assignment 4. So for an incompressible flow, if the local area velocity decreases, the dynamic pressure will. The dynamic pressure is nothing but Q, right? So you have Q is equal to half rho V infinity square. So if the local area velocity decreases, what will happen to Q? Decreases, yes. It's fairly straightforward. Wave drag is produced due to, actually the first and second options are more or less the same, so it cannot be that. What could it be? Wave drag, as the name suggests, due to shock wave formation, yes. But why? Why is there a drag when a shock wave is formed? The answer is right. There is a drag, additional drag that is produced when the shock wave is formed. Why? Why is there an additional drag? Okay, so there, yeah, I think you can say it a bit clearer. So let me just try to show you the image. Yeah, so there is a shock wave that's created here. After that, there is, in the wake of the shock wave, there is a turbulence. And the turbulence is not smooth. Like he said, it's not smooth. It causes skin friction drag. All are the forces here, they are not smooth. So they have some additional skin friction drag terms, which is why you have additional drag components when the flow is encountered with a shock wave. Also, the large pressure differences across the wave. All of these factors contribute towards this possible flow separation. But when this shock wave progresses over the surface of the airfoil, there is a definitive flow separation, and there is vortices generated here and turbulence, which causes drag on the surface of the upper surface of the airfoil. And as the shock wave progresses, you also have shock waves that are generated on the lower surface, and similar conditions are encountered below as well. So you have additional drag components. So wave drag is associated with shock wave formation and due to the possible flow separation. Okay. Supercritical airfoil is primarily used for higher divergence Mach number, more lift coefficient, higher stall angle, or higher critical Mach number. What is it used for? This is a slightly ambiguous question, I believe, because it makes both the critical Mach number and the drag divergence Mach number higher, but it's more the higher drag divergence Mach number, right? Yes. Okay. So we studied what the supercritical airfoil is. The advantages of the supercritical airfoil were listed. This was discussed in the previous session. So one of the advantages is that it has a higher drag divergence Mach number. What was drag divergence Mach number? Both of them. What was critical? What was M critical? And what was M drag divergence? What were these two? Can someone tell me what were these two Mach numbers, critical Mach number and drag divergence Mach number? Yes, correct. And critical Mach number? Okay. So critical Mach number is the free stream Mach number at which at some point on the airfoil it has encountered sonic. So it has encountered Mach 1. So a shock wave is formed. So it is the free stream Mach number at which some point on the airfoil has supersonic flow. Okay. And drag divergence Mach number. So you remember the graph went something like this. So this point, this is M critical, and this is drag divergence Mach number at which it starts increasing exponentially somewhere here, not here, somewhere here. Okay, and this is your Mach 1. Okay, so one of the advantages of supercritical airfoil was that it has a higher drag divergence Mach number. It has the shock waves forming aft of the airfoil when compared to other airfoils. So typical airfoil was a typical cambered airfoil, had such an orientation, such a configuration geometry. So this is where, suppose this is where the shock wave initially is formed at critical Mach numbers. For a supercritical airfoil, so the top surface is flattened and your camber is only encountered towards the trailing edge. So you have something, okay, let me just draw it again. So you have a flatter surface and the camber necessary is towards the trailing edge, right? So the shock wave is formed later on the upper surface. Can all of you just mute yourself? I think someone's mic is turned on. Okay. So the supercritical airfoil has a flat upper surface as compared to a typical cambered airfoil, because of which the first shock wave is formed way aft on the upper surface as compared to the cambered airfoil. Okay. What happens here is that your supercritical or supersonic flow is delayed. It doesn't encounter it somewhere closer to the leading edge, it's later. Because of which there is reduced boundary layer shock interaction. So this boundary layer separation, all of that happens further aft on the upper surface, and there is a lesser interaction between the boundary layer and the shock wave, which leads to lesser drag. Okay, it also gives you a thicker wing, which means lighter wing. This is something we discussed in the last class again. If it's a thicker wing, it is more hollow, which is why it is lighter, because you need less reinforcements to support the wing, withstand a lot of forces. Somebody is constantly turning on their mic. Okay. So moving forward, the next question was, which of these techniques is employed to delay the critical Mach number? So you had a supercritical airfoil for delaying the drag divergence Mach number. What about critical Mach number? Was it increasing the thickness of the airfoil? Was it increasing the sweep on the wing, increasing the camber, or decreasing the drag divergence Mach number? Decreasing the drag divergence Mach number decreases your critical Mach number. I think somebody is joined. Yeah, okay. So, which of these techniques is employed to delay the critical Mach number? Was it increasing the thickness, increasing the sweep, increasing the camber, or the drag divergence Mach number, or decreasing the drag divergence Mach number? So we just saw that it cannot be this, because when you decrease the drag divergence Mach number, your critical Mach number also decreases. What else can it be? What else can it be? When it says delay the critical Mach number, it means yes? Yes, yes, correct. Can you try to tell me why? Why swept wing delays the critical Mach number? So if this is your fuselage reference line, your regular airfoil wing was something like this. Now you have a swept back wing. So you have something like this. Yeah, Can you try to tell me why it is the swept wing that delays the critical Mach number? That is the right answer. Can you just try? Yes. Okay. 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 So let me, I think I have a figure that explains this. Yeah, okay. So your wing without sweep has the same velocity that throughout all airfoils throughout the span of the wing encounter. So the normal velocity that each section or each airfoil section of the wing encounters is the same. It is the same throughout. So it's the same as u here is just v. So the normal component is always v infinity. Throughout the span of the wing, each airfoil section encounters the same normal velocity component. When you sweep it back, at each cross section or each airfoil cross section, the normal velocity component is changed. So here you have a sweep angle of say 45 degrees. You have the normal component is so Vn is V infinity cos 45. So what happens is that the effective velocity that each airfoil sees is reduced by a factor that is corresponding to the angle, which will always be less than the free stream velocity. Okay, so each airfoil section throughout the span of a swept wing, encounters a normal velocity that is less in magnitude as compared to v infinity. What happens here is, suppose if v infinity was v critical corresponding to critical Mach number. Okay, so if it was v critical, now if it was a straight wing, you get v critical, it reaches critical Mach number, some point on the airfoil you have supersonic flow, and all of the other disadvantages associated with it follow. So if you have a swept back wing, each component progressing along the span of the wing has a lesser velocity encountered, which is less than, so Vn here is less than V critical. That means if at the root it encounters critical Mach number, that means somewhere on the root there is a supersonic flow. But further down, further along the span of the wing, Vn is less than V critical, hence there is no supersonic flow over that cross section. So though there is a supersonic flow at the root chord, there is no supersonic flow at the tip chord, or it is delayed. Okay, so it takes a little more time for the supersonic flow to occur at the tip. So a swept back wing delays the critical Mach number. So it allows you to fly for a larger range of Mach numbers till the supersonic flow is hit. Okay, so is that clear? Do you need me to explain? Okay, okay, thank you. The next, yes, yeah, sure, sure. Just tell me when you're done, okay? So each normal component, each airfoil section has a lesser velocity encountered. So you have a larger range to operate, larger range of Mach numbers to operate. Are you done? Okay. Yeah. So the next question is, what is the relation between the drag divergence Mach number and critical Mach number? So we had shown that diagram, just the graph. Yeah. So this was the graph. Just keep that in mind, and we'll just look at this question. So is m drag divergence Mach number, is it equal to critical Mach number? No. Is it greater than critical Mach number? Or is it less? Or you have no relation between those two? Correct. Absolutely. So this was the graph that I was referring to. So this is the point where at some point on the airfoil you have a supersonic flow, and your drag divergence Mach number, like he mentioned earlier, is the point where the drag exponentially or rapidly starts increasing to the maximum, which is at Mach 1. Okay, so this is the relation. MCR is less than M drag divergence is less than Mach 1. Okay, okay. What is the thickness of a NACA 0002 airfoil? This is simple. We had studied the force. Yes, so last two digits represent the thickness to chord ratio. In this case, it's just 0.2, which gives you 2%. Right. So just a recap of the airfoil series, what each digit represents. The first digit represented the max camber in 1/100th of C. The second digit represents the location of maximum camber, the location of this maximum camber in 1/10th of C. Okay, this was an error that I had to fix. Okay. And the third and fourth digits give you the maximum thickness in 1/100th of C, which is what we used to calculate for this previous question. What is generally given in a swept back wing to avoid tip stall? Wash in, wash out, flap, or none of these? It cannot be a flap because flaps are just high lift devices. It is not there to serve any other purpose. Washout, yes. Again, can you try to explain what is a washout? Correct, correct. Absolutely right. So what happens is that the incidence angle at the wing root is higher than the incidence angle at the tip. So what happens is that at the root you have a higher incidence angle, the wing setting angle. So if this is your fuselage reference line, your wing setting angle at the root chord is higher as compared to at the tip. So at the tip it is either negative or lower than the wing root. The reason that he said is absolutely right. So even if your root stalls due to the lesser or due to the negative twist at the wingtip, the wingtip will not be stalled. So you will still have effectiveness of the wing for a larger range of alphas, even if the wing root is stalled. So your wingtip will be stalled, not much later, but you will still have a range over which you can fly even though your root is stalled. Okay, so the incidence angle at the root, it's much higher than the incidence angle at the tip. And the reasons over here explained perfectly. Okay, this is something we have gone over. What is a reflexed cambered airfoil? Third option, yes. What is the benefit of a reflexed cambered airfoil? Exactly. And why do we need Cm naught to be positive? Okay, okay, so your Cm, that is pitching moment equation, is Cm naught plus Cm alpha into alpha. The only condition for static longitudinal stability is that Cm alpha should be less than 0. Cm naught greater than 0 is not a condition for static stability. This is for static stability. This is not for static stability. There was another reason. What is the other reason? So we know our graph, that is Cm versus alpha or Cm versus Cl, is something like this. So this is Cm. Yes. That was supercritical airfoil, right? Not reflex. Yes. Okay. So supercritical airfoil had a flatter upper surface and camber towards the end. Now your reflexed airfoil will be something like this. Okay. So you have a curve up towards the trailing edge. That is right. The answer is that it is done to ensure Cm naught is greater than 0. But my question is, why do we need Cm naught greater than 0? Why do we need this to be a positive quantity? This is Cm naught. Why can't we have a curve like this? This is also Cm alpha less than 0. which is the only condition we need for static stability, why can't we have Cm naught negative? Your voice is breaking. I'm not able to hear your answer. Can you try again? You were getting it. Okay, okay. So I think what you said is the right answer. What you said was that we wanted to trim at a positive angle of attack. So if it is below, it will trim at negative angle of attack, which is not desirable. If it is a positive Cm naught, it will trim at positive angle of attack. Okay. So which is why we require Cm naught. We prefer Cm naught to be positive. Okay. So for condition for stability is only this. Static longitudinal stability condition is only Cm alpha should be less than 0, not this. Okay, this is to trim your aircraft at positive angle of attacks. Okay, so this is just, we just go over all the airfoils that we discussed in the previous section. So this was your supercritical airfoil and this is your reflexed camber. Supercritical airfoil, as you can see, thicker, we had discussed this, thicker, lighter. Reflexed cambered airfoil has this curvature, upward curvature towards the trailing edge. It will compromise on the lift generated of a regular cambered airfoil, but this is essential to ensure Cm naught is positive. Okay. Next question is similar to the one that we had discussed in the previous question, but we had done that for symmetrical airfoils and tails. Here it is, first statement is most of the wings use cambered airfoils, and the reason they have stated is that cambered airfoils can produce positive lift at zero angle of attack. Are both the statements true? And is the reason the correct reason for the first assertion? Yes. So the yes. So the correct answer is this. So just to show you that uh, this was the lift curve slope of a symmetric airfoil, CL versus alpha. For a cambered airfoil, it will be something like this. So even at zero angle of attack, you will have a lift generated, which is desirable for wings. Wings are the main bodies that generate lift. So it is desirable for the wing to produce lift even at zero angle of attack. Okay. Okay. So for a cambered airfoil, Cm naught is, we just discussed this. For a cambered airfoil, Cm naught is, for a positively, when they say cambered, it's just positively cambered. It's always negative. Yes. Can you tell me why? Why is it negative? So I'll just draw the cambered airfoil here. This is the AC. So you have a pitch down. You just said it's negative, so it's nose down, pitch down. It's Cm naught negative. Why is it negative? Why is it always negative? For a cambered airfoil, why is it negative? Why is it always negative? Just try. I think I've discussed this in almost all three of the sessions. So what is aerodynamic center? Where the net effect is zero, so there are no lifts, no forces at the aerodynamic center. Yes, that is the right answer. It is the point at which the moment is constant with change in alpha. So at what point do we usually, or at what point is force actually considered to be generated? the lift and drag forces, the aerodynamic forces are, yeah, we do our analysis at the aerodynamic center, so we transfer our forces to the aerodynamic center. But where is it generated? At what point? So for convenience of our analysis, we transfer the forces to the aerodynamic center. So you have lift and drag, but they are not considered to be generated here. We transfer it to the aerodynamic center, right? From where are we transferring? CP, exactly. Center of pressure. So for a cambered airfoil, your center of pressure is always after the aerodynamic center, which is why when we transfer the forces to this aerodynamic center, you have a negative moment, which is why your Cm naught or the moment m naught is always negative for a cambered, positively cambered airfoil. Okay, so your center of pressure initially had the lift and drag forces, which we transfer to the aerodynamic center. When we transfer forces to another point, it comes with a moment. And that moment here is nose down, which is negative, because your aerodynamic center for a cambered airfoil is ahead of the center of pressure. Okay, which is why your Cm is always negative for cambered airfoil. Okay. Now, wing aspect ratio is defined as AR is, okay, span squared multiplied by, yes, p square by s. Okay, so yeah, so I had made a mistake in the first session. I think b is the span and s is the area, the reference area. Okay, okay. So yeah. What do winglets do? What are winglets or wingtips? What are winglets? Yes. Induced drag. Okay, so from the options given here, you're right, it reduces the induced drag. From the options given here, what do you think the right answer is? Induced drag happens why? Due to? Okay, so yes, exactly. So if your wing is something like this, so the flow coming from below and the flow coming from above interact at the tip and vortices are generated which keep traveling downward the flow. Okay, so there is a turbulence created here. Wing tips, like he said, the curved edges, curved up edges of the wing tips help reduce the turbulence at the tips. Okay, so it reduces this interaction or it smoothens out the flow. There will obviously be a turbulence, there will obviously be vortices generated, but it reduces it by smoothing out the flow. It doesn't ensure, I mean, it makes sure that the velocity coming from below and above the wing surfaces do not at a point interact. Okay, so it's gradually makes them interact. What happens is that it reduces the turbulence at the tips, like he said, reduces the interference drag. Okay, so you can see this is an image that I had shown in the first session. So this is why, because of the interaction between the upper and lower surface velocities or the airflow, you have vortices generated, and these vortices travel downward along the direction of the flow, okay, from the wing tips. So now when you have, if there are no winglets, this is a large vortex because at one point suddenly both the flows interact and there is a turbulence and there's a vortex generated which travels downward. If there is a winglet, so that sudden interaction happens only at this small tip. So you have smaller turbulence, smaller vortices generated, which I think you can see clearly here. So if there is no wingtip, there are large vortices generated because that entire edge contributes towards this interaction, and there are large vortices generated. But if you have a wing tip, something like this vortices are generated only at this wing, that point. So your amplitude of turbulence, amplitude of disturbance, all of them are reduced. The vortices are smaller, and the interference drag is reduced. Okay, so that is the purpose. So it reduces the turbulence at the tips and reduces the interference drag. That is why we have the winglets. Okay. Now, determine the tail volume ratio of the vertical tail given wing area, wingspan, mean chord, vertical tail arm, vertical tail area. So they've asked you to find VV. What is the formula? Vertical tail volume ratio. What is the formula for vertical tail volume ratio or horizontal tail volume ratio? We've never encountered vertical tail volume ratio so far, but we have seen VH. Can you tell me what VH is? Yes. What is the formula? Okay. And for vertical tail, since the reference area will be SVL. Yes. So here it will be B. For a vertical tail, the reference span is B. For horizontal tail, it is the chord of the wing. Okay. So now that we have this formula, just calculate and tell me what will it be. SV is 1.25. LV is 3.25. S is 10.35 and B is 10 meters. What is the value? Can you just calculate and let me know? Okay. Okay. Did everybody get the same answer? Did all of you get the same answer? Yes. Okay, so 0.039. Okay. Primary control for spin recovery is, what is spin? Spin is one of the uh, not turbulences, kind of a stall encounter. Yes. Yeah, okay, the answer is rudder, but can you tell me what spin is? Yes, that is right, absolutely right. Comes down like a spiral or comes down in a helical path. But why does this happen? Okay. Uh, okay. You're right about how it goes down. It goes down in the spiral path. That is right. I had mentioned that the spin is a kind of a stall. So can you take a hint from that and try to tell me how spin occurs? It's a kind of stall. Okay, let me try to explain it. Okay, so spin occurs only in a stalled aircraft. What is a stalled aircraft? When both the wings have crossed your stalling angle, alpha stall, it has crossed that, it is at an angle higher than the alpha stall. So alpha of both wings is greater than alpha stall. Okay, like he said, it moves down in a helical path or spiral path. So both wings are stalled, but one wing is more stalled than the other. Okay, so when this happens, your aircraft enters into spin. Why? Because the more stalled aircraft, so if you take the inside of this helical path, this wing is more stalled than this wing. Okay, so this wing is more stalled than this wing. So if it's more stalled, what happens? The lift increases is more than, okay, let me just, okay. So if this is the more stalled wing, is the lift on this wing higher than this wing or lower? Lift 1, yes. So lift 1 is lower than lift 2. So it dips, right? It dips into the spiral. It dips into the axis of the helical path, and it keeps going such a way because it's progressively lesser than this wing. So it keeps following that path. Now, how do you recover from the spin? So the process, yes, exactly. So this is the most important step where the rudder is put in the complete of with its full rudder deflection in the opposite direction to the spin. So the sequence which you're supposed to follow when the aircraft encounters spin is called pair, where first you set your power to idle, take out all the power of the aircraft, then you put your ailerons to neutral. Why you put ailerons neutral? Because when it recovers, it will recover after this step, but when it recovers, you need both your wings to have the same angle of attack. So if your ailerons are unbalanced, each wing will still have a different angle of attack, and it will have a chance to continue down that spiral or a different spiral. So you need to neutralize your ailerons, that is, make both the angle of attacks the same. Then you put your rudder in the opposite direction, deflect your rudder completely, full rudder deflection in the opposite direction. Then you ensure after it has recovered, so at this stage the recovery has started, then you reduce your angle of attack at both the wings so that it is no longer greater than stall. So at this step, what happens is alpha wing less than alpha stall. Okay. So then both of your wings are not stalled. Both of your wings have the same angle of attack as per this step, and both of your wings are not stalled. So it will recover from the spiral or the spin. So you've understood what spin is? Yes. So it only occurs when both the aircraft is already stalled, that is both the wings are stalled, but it happens when one wing is more stalled than the other. So the more stalled wing loses its lift much more faster than the wing that is less stalled. So it continues down a spiral path. Okay. And how do you recover from it? You set your power to idle, make your ailerons neutral. Then the most important step, rudder, you deflect it completely in the opposite direction. Then to ensure that your aircraft is no longer stalled, you deflect your elevator. Okay. Okay. Why dorsal fins are used? What are dorsal fins? What? Yes, yes. So that is right. Why are they used? Okay, yawing stability. But what happens if you don't use it? Yeah, so if you use it, it increases the stalling angle, right? Yes, correct. So the answer here would be what? From the, yes, exactly. To improve the tail effectiveness at high side slip angles. Okay, this is a typo. It should be side slip angles. Okay, so this is an example. So this aircraft has a dorsal fin. This part is a dorsal fin. This aircraft, which is very similar to the previous one, does not have that. Okay, so it has a constant sweep throughout the vertical stabilizer. Here you have a differential sweep. In this dorsal fin, you have a higher sweep as compared to this regular vertical tail. Okay, so let's see. Okay, that is a dorsal fin. Okay, this is beneficial only in high side slip situations, which is why not all aircrafts have it. It is an optimization. You have to decide whether you want it or not. So it is only beneficial in high side slip situations. In high side slip situations, what happens? So this part of the aircraft stalls, right? And then you have no yawing direction control or stability because this part has encountered stall. So you have another section here which has a higher sweep angle. It's swept back more. So higher sweep back angle, which allows you This portion of the vertical stabilizer allows you to have your control, your stability. Okay, so it is only beneficial in high side slip situations. What are high side slip situations? One is of course the crosswinds, high crosswinds while takeoff landing. But what is the other situation? What other? Yes. Sorry. In spin. Uh, okay. Okay. But what else? What else can you think of? Okay. So if the engine's on one side of the, okay, coordinated turn, side slip angle. Okay, fine. Okay. What happens? Okay. Turn is something that we intentionally do, right? So, what about unintentional cases? Crosswinds, yes. One example would be if the engines on one side of the wing fail, right? So you have thrust produced only in one side and it will tend to keep turning the aircraft, which will have high side slip situations. So to negate that, you need to be able to have more stability. Your vertical tail needs to have more effectiveness, right? So there the side slip angle increases beyond what your regular uh, vertical tail can handle. In such situations, your vertical stabilizer, the dorsal fin has a more range of operational, has a more operational range, right? So it helps you stabilize and control the aircraft in high side slip situations. Okay, so the answer was to improve tail effectiveness at high side slip angle. So it increases the range of side slip angle at which we can operate. Okay. Find the degree of elevator float. Consider tail angle of attack is 2. CH delta E is minus 0.005. CH alpha T is minus 0.0052. What is elevator float and what is the CH? What is CH? Uh, okay, this is dCH by d delta E. What is this CH? Okay, yes. So, hinge moment coefficient, correct. So now can you tell me what is elevator float at what? So hinge moment is CH, right? So it is CH naught. Since it's usually symmetric, we will not have a CH naught. We'll have CH delta E into delta E plus CH alpha T into alpha T. So what is elevator float? Angle of elevator float? When you leave the elevator, when you don't hold it, when you leave it, so it is allowed to freely float. So at that point, what will be the hinge moment? When you allow your elevator to just float freely, you're not holding it at any particular point. So what will the hinge moment be at that point for such a condition when you allow the elevator to float freely? Exactly, hinge moment is 0. Okay, considering 0 first. Okay. So in such a case, this is float. So for float, you have CH equal to 0. So if you substitute all the values there, you get delta E float equal to minus CH alpha T by CH delta E into alpha tail. So what is this value? Minus CH alpha tail is 0.0052 and this is minus 0.005 into alpha tail is 2 degrees. Doesn't matter here if it's degrees or radians because this is a ratio, they're the same term, so it cancels out, so it can be degree or radian. Since it's given in degrees, so your answer will also come in degrees. What will the value be? Just calculate and tell me. 0.0052 divided by 0.005 into 2. So it's minus 2.08. Right, so this is the answer. So if you leave your elevator to float freely, it will float at this angle. Okay, that's what it means. So there is no hinge moment. Okay, so these are the equations that we have used. Like I said, for float, your CH is 0. There is no hinge moment, H is 0. And delta E float. This is CH delta T by delta T. So alpha T was the tail angle of attack. Delta E was the elevator deflection. What is delta T? Trim tab. Okay. Yes. So since the question has no trim tabs, we have negated this term and we assume symmetrical airfoil. We negated that term. Okay. Next question. Hinge moment coefficient depends on. So we just saw the equation here. This is the hinge moment. Hinge moment coefficient is here. So what does it depend on is the question. Look at the options. Tail angle of attack, elevator deflection, only tail angle, only wing angle. Exactly. First option. Hinge moment depends on all those parameters. Depends on tail angle of attack, elevator deflection, trim tab deflection. Okay. Okay. What is the aspect ratio of a wing with span 11 meters and chord 0.62 meters? Assume rectangular wing. So aspect ratio formula was what is the formula for aspect ratio? Okay, yes. So in this case, it is B by C. Yes. So, okay. 17.7. Previous slide. Okay, yeah. Yes, are you done? Okay. So I'm moving ahead. Okay. So now that we have some time, let's study something new. So it's the aerodynamic center calculation. Okay. So these are some of the empirical formulas that we will be using to come up with an estimate of the aerodynamic center, mean chord line, all of those. Okay. Just a minute. Okay. So this is the location of your mean chord. So C bar, mean chord that we use throughout in all of our expressions, we use C bar, which is the mean chord length. Okay, so it's not the chord at the root, it's not the chord at the tip, it is the mean chord length at the aerodynamic center. So we need to find out that location. For aerodynamic center, we need to find out the location X and Y. Okay, so now CR is given, root chord is given by CR, tip chord is given by CT, and your X. So this is your mean aerodynamic chord. So now your aerodynamic center from the leading edge of the mean aerodynamic chord will be at what point? So if this is your leading edge of the mean aerodynamic chord, at what point will your leading aerodynamic center be? From the root, it is at distance YMAC. So what is XMAC? What is this location? It's the quarter chord point, right? So your aerodynamic center lies at C bar by 4. So this is C bar by 4. It lies at this point. This value is X MAC. Okay, right. So this formula we already know. Aspect ratio is equal to B square by S, where B is the span, S is the area, reference area. Taper ratio lambda is given by CT by CR. CT is tip chord and this is root chord. Okay. Now to find out C bar, this is the empirical formula that we use. 2 by 3 CR 1 plus lambda plus lambda square by 1 plus lambda. Now, for a rectangular ring, if there is no taper, what will this taper ratio be? So, lambda for rectangular ring will be what? 1. And if it's a triangular ring, 0. Did everybody get why it's rectangular is 1 and a triangular is 0? Yes, okay. So, what will the C bar for rectangular wing be? Just plug in the values. C bar lambda for rectangular is 1. So, it is 3 by 2. This is 3 by 2. This is CR. And this is 2 by 3. So, lambda C bar for rectangular wing is nothing but the root chord. Okay. And for a triangular wing, it will just be this. Okay. Similarly, YMAC formula is given by this B by 6, where B is the span, lambda is the taper ratio. Okay, so now let's try solving a simple problem. So this is what is given to you, the root chord, that is CR, taper ratio is 0. That means what is the shape of the wing? Exactly, triangular. Triangular. Okay. Half span, that is this is B by 2 is 0.5 meters, and taper axis is mid chord. So when they say taper axis, so your wing can be, triangular wing can be like this. It can also be like this, right? So, okay. So both of these are triangular wings. When they say taper axis is mid chord, which one do you think is the wing that they are referring to? Taper axis. At about what axis is the tapering occurring? Mid chord, yes. So second option, exactly. So if it is this, what will they say? What will the taper axis be? Okay, so here it was mid chord, right? So mid chord is this. Okay, so it is tapering about this mid chord, right? So it's this. This taper is occurring about the mid chord. Here the tapering is occurring about. Okay, isn't it occurring about the trailing edge? Taper axis is, it's tapering to the trailing edge. Here it's tapering to the mid chord. Okay, that is how it is defined. So it's tapering to the mid chord, hence the taper axis is the mid chord. Here it's tapering to the trailing edge, so taper axis is trailing edge. Okay. Okay. So now they've asked you to find out AC, that is the aerodynamic center, and yes. Okay. So since this taper means reduction. Okay. So it's tapering to the trailing edge. This is the oncoming velocity v infinity. So this is the leading edge, and this is the trailing edge. Since it's tapering to the trailing edge, the axis is trailing. Taper axis is trailing edge. Now since this is tapering to the mid chord, this is for each chord line, the midpoint is here, right? So this is the mid chord line. Since the taper is happening towards the mid chord line, the taper axis is mid chord. Okay, here it is mid chord, right? So if you had say something like this, and the oncoming velocity was here, what will the taper axis be here? Where is it tapering towards? It's tapering towards this line, right? What? Yes. So the taper axis here is the leading edge. Now if they say taper axis is say quarter chord point, so it will be like this. Right? So this is tapering about the quarter chord point. This is C bar by 4. Okay? Is it clear now? So this is taper axis is quarter chord. Okay. So now they've asked us to find aerodynamic center and aspect ratio. Aerodynamic center, you need to find both XAC and YAC. So the wing, let me just go to so this is the wing that we will be looking into. So YAC is this value. XAC is, first you take quarter chord, that is C bar by 4, and its value from the root leading edge. So this is XAC. So when they ask you to find out AC, you need to find out both XAC and YAC. Okay, so let's try to solve this question. Okay, using the formulas that we know. Okay, so when I say XAC, XAC is what? I'll just draw that again. This was C by 4. I bring it here. So this is the aerodynamic center. Okay. So Y value we get directly from this equation. For XAC, you need to find out this distance. That is XAC. So what is XAC? How do we write it? I'll write the equation. Just tell me if it's right. Okay. You are measuring it from the leading edge, root leading edge. So you're measuring it from here downwards. Okay. So CR by 2 minus C bar by 2. So when from this line, if I take CR by 2, it is this entire line, right? If I subtract C by 2, I get something over here, right? Let me just draw this again. Yes. 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 Yeah, so the final equation here will be, there'll be plus some term here. Okay, so I want you to tell me what it will be. So your it will form a rectangle. So what I'm trying to find out is, so let me just erase this. This is your aerodynamic center. Okay. Okay. So both XAC and YAC have to be measured from the leading edge and the root chord. So YAC is this value, right? XAC has to be measured from the leading edge. So this value, this entire is your XAC, right? Now if I find out C bar, I can get this small point as C bar by 4. This length is C bar by 4. What is this full length? This whole length. This whole length. Let me take another color. I can't do that. Okay. So this small, okay, I should not take blue. So this value is C bar by 4. The one in green is C bar by 4. Okay. Why will it be C? Yes, the green color, that length is C bar by 4. What is the red length? It will be C bar by 4 plus some quantity, right? Will CR by 2 is this entire length. Okay, let me try to use different colors. Okay, so this is your aerodynamic center. Let me just draw this. Okay. The one in green is C bar by 4. Okay. Now, let me take yellow. The one in orange is CR by 2. Is CR by 2. Yes? That orange line is CR by 2. Yes? Okay. So what we need to find out is this distance, right? So another color. What the unknown part of that is only this purple line. What is this purple line? What is the length of the purple line? So what we need to find out is this entire red line, right? So what is this purple line? Purple line will be CR by 2 minus C bar by 2. Am I right? Right? So your final, that XAC given by the red line will be C bar by 4 plus CR by 2 minus C bar by 2. Correct? This quantity plus this quantity. So here it will be C bar by 4. Right? Okay. So let's just simplify. Okay, from this equation we can find out XAC, but we don't know C bar. So let's try finding C bar, which is 2 by 3. CR is given as 1 meter. Taper ratio is 0. So this will be 1. This value will be 2 by 3 is 6. Okay. So substitute this C bar value into this equation. So you get 1. CR is 1 by 2 minus 0.667 by 2 plus 0.667 by 4. What is this value? What is that value? What is the final answer? Okay, 0.5 minus 0.667. What is the numerical value? .33, right? So keep that there. Now find out YMAC, which is B is given by half span is 0.5, so B is 1 by 6 into taper ratio is 0, so this is 1, it's just 1 by 6, so it's 0.1667 meters. Yes, YAC is the location, so this is your aerodynamic center, it's the Y coordinate of the aerodynamic center from the root chord. Yeah, we need to yes, from the root to the aerodynamic center. XAC is from the leading edge of the root tip to the aerodynamic center. So this is XAC. Okay. So we need to find out both of them. When they ask you to find out aerodynamic center, find out both X and Y coordinates. So when AC is asked, XAC is we have calculated as 0.3 and YAC is 0.1667. Then they've also asked us to calculate aspect ratio, which is B square by S. B is given to us as 1. What is S? S is the area. So what will it be? It's the twice the area of this triangle. So what is the area of 1/2? Twice the area of the triangle. So what is the area of the triangle? What is the area of half? Half? Yes. What is the length? Yes. What is the breadth and what is the height here? Okay, CR is 1 and height is? Yes, half span, exactly. So 0.5. So this is the final answer. What is the answer? Just calculate it. One divided by 0.5 is 2. So aspect ratio is 2. Yes. Okay. So is this clear? How we calculate the aerodynamic center? Yeah, sure. Just let me know when you're done, okay? So the only tricky part about this is the XAC. I think that is clear now. We'll just try another problem. Shall I move on? Yeah, sure. Yes, quarter of the mean chord. Yes. But from the leading edge of the root. Yes. Okay. Let's move on. We'll try another problem. So now they've given you root chord. So this is CR. They've given you tip chord. So in this case, your taper ratio will not be 0. Span. And they've given you trailing edge as the taper axis. Okay. So how will your wing look? So if this is your root chord and your tip chord is given, so how it's tapering about the trailing edge. So how will your wing look? Where should I place my trailing edge, the tip chord? So it's tapering about the trailing edge, right? So this is the trailing edge. Now the tip chord is here and it is tapering. It's the delta wing, yes. So this is how the wing will look, okay? Taper axis is the trailing edge. It's clear now about the taper axis. It's the axis towards which it tapers. So now they've said its tapering axis is trailing edge. You can see that it tapers towards the trailing edge. Okay. Now they've asked you to find out again AC, aspect ratio, and the leading edge sweep angle. Leading edge sweep angle is this angle. Okay. Okay. So let's just proceed. So I've just made the figure. This is the figure of the wing. Okay. So now let's try finding out the quantities. Again, starting with XAC. XAC. What will it be? Try telling. So something like this. So this is your aerodynamics. Mean aerodynamic chord will be CR plus CT by 2. Will it? Yes. So let's just proceed how we tried in the previous problem. So this is your C by 4, right? This quantity alone. Now just add this quantity to it. So we have to find out that value. So we have your C bar by 4 plus what? Yes. Will it be CR by 2? CR by 2 will be somewhere here, right? This is simple. It's simpler than the previous case. So this entire length is CR, right? And short length is C bar. This is CR and this is C bar. It's just CR minus C bar. Yes? Is it? Yes, yes. Tell me. Okay. Okay, yes, yes. You're right, yes. Okay, yes. Uh, let me just tell me what will it be again. So it'll be CR by 2. Hmm. This entire C bar by 4, right? So won't that just be this length? But we need the length from the leading edge of the root, right? Yes. This will give you. Okay, so XAC is from the leading edge of the CR, that is leading edge of the root. That is how we define our XAC. You're right about, I think you're right about this. We'll verify our answer. Like we can calculate C bar from this and C bar from here. But if I just divide this by 4, it will give me just C bar by 4, which is just this quantity. But we are taking our reference to be the leading edge of the root. Yes? Okay. So, okay, we'll verify if this is right. Okay. So let's just calculate CR plus CT by 2. How much will it be? CR is 0.9 plus CT is 0.15 by 2. Can you just tell me how much it is? Okay, so it's 0.525. Now let's calculate C bar from this formula. C bar is 2 by 3. CR is 0.9. What is the taper ratio here? Taper ratio is CT by CR. Yes. Okay. So let's just find that value. 0.15 divided by 0.9 is 0.16. So you have 1 plus 0.1667 plus 0.1667 squared by 1 plus 0.1667. Can you calculate this and tell me? 0.667 plus 1 divided by 0.667 into 0.9 into 2 divided by 3. Can you just calculate and tell me? It's coming to 0.6, right? Something around 0.6. Why is that different from CR plus CT by 2? Okay, let me just check why this is there. I'll let you know in the next class. So I'll just let you know in the next class. But we'll proceed with this equation now, okay? So it's 0.6. If you substitute this C bar into this equation, what do you get? You get 0.6 by 4 plus CR is 0.9 minus C bar is again 0.6. What is this value? 0.6 by 4 plus 0.9 minus 0.6. 0.45. Yes? Is that the right answer? Okay. So now let's find out YAC. So its B span is 1.75 by 6. And you have 1 plus 2 into 0.1667 by 1 plus 0.1667. What is this value? Can you hear me? Am I audible? I'm not getting any response from you guys. Okay, okay. So can you calculate this and let me know? 667 plus 1 divided by into 0.75 by 6. So what is this value? Just let me know. I'll wait for you. What is the value? What is the value? It's a simple calculation. Just let me know. Yeah, yeah, sure, sure. Take your time. What about the others? Are you also doing this? So when they ask aerodynamic center, you find out XAC and YAC. YAC is, what is the value? I'm just going to write it. Just see if the answers are matching. So that's 0.33 meters. So that gives you your AC. Next is aspect ratio. Aspect ratio is B square by S. Now B is given to you as 1.75. So 1.75 square by S. What is the area of the surface? How do you calculate the area of the surface? Just tell me the formula or the values. Yes. 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 So what two parts? So one, this is how I would divide it. You can divide it in like different ways. So I am taking, okay. So let me know the two areas, area of this rectangle and area of the main triangle. Can you just tell me the two areas? Area of the rectangle would be, area of the rectangle would be, CT is 0.15 into 1.75. Okay, this is the rectangle and the triangle would be half. What is the base? 1.75 into height is 0.75. So 0.75 is CR minus CT. This value 1.75 So I'm getting it to be around 3.3. Just let me know if anything is wrong. Then they've asked you to, you found out aspect ratio, then they've asked you to find the leading edge sweep angle, which is this angle. So tan of that angle would be, what would the value be? What is the tan of that angle? What is the tan of the sweep angle? What is the tan? Tan is opposite side by adjacent side. What is the opposite side? What is this value? Yes. Okay. So your sweep angle 0.75 divided by 1.75 by 2. Tan inverse angle is around 40 degrees. So it's 40.6 degrees, right? So we have also found out the leading edge sweep angle. Is this clear? Are these two aerodynamic center calculations clear? If there's any question? Okay. So can I go on to the next slide? So now we'll try to find out the neutral point of such a configuration. So what we can see here is there are two wings, one high wing, one low wing, right? So this is wing number 1, wing number 2. This is a canard and this is a tail. Okay. So and these are the values given to you. And the distance between the trailing edge of the canard and the leading edge of the wing is 1.5 meters. Distance between the trailing edge of the wing and the leading edge of the tail is 0.5 meters. Okay. Yes. This is trailing edge, right? Trailing edge of the wing to leading edge of the tail. Okay, and this is trailing edge of the canard to leading edge of the wing. Okay, so these two. Yes, but the question has given you these dimensions. Okay, we will be measuring all of our aerodynamic centers, neutral points, CG location, everything from the leading edge of the wing, but the question has given you these dimensions. This is what is available to you in the question. Okay? Okay. And they've also given you some of the aerodynamic and geometric parameters. So the wing has CL naught of 0.3, CL alpha of 6, Cmac, Cm at the AC as minus of 0.1. What will the Cmac of these two be? Canard and tail? What will it be? 0. Can you tell me why it will be 0? Yes. So since CL naught of canard and tail are both 0, they are symmetrical airfoil. Symmetrical airfoil has 0 pitching moment coefficient at the aerodynamic center. Whereas for a positively cambered airfoil, your pitching moment coefficient is negative. Okay. Then they've given you the span of each wing. Then they've given you the Oswald's efficiency factor, the root chord, and the tapering ratio. Okay. For each of the wing, tail, and canard. So the wing has taper a ratio of 0.5, canard has taper ratio of 0. What does that mean? What? Yes. And what about tail? Exactly. Okay. Now let's try to find out the neutral point. Prior to using these values, let's try to find out the neutral point. These, like you had mentioned, we measure all our quantities from the leading edge of the wing. So if the aerodynamic center, somewhere here, okay, so aerodynamic center of the wing is measured from the leading edge, aerodynamic center of the canard is measured from the leading edge of the wing, and aerodynamic center of the tail, and XCG and XNP. What we are required to find out is XNP. Okay. This figure in mind, we'll keep coming back to it. So let's try to derive an equation for x and p. How do we begin? We begin by taking the moments about the CG. Okay, we'll take the moments about the CG. Let me write it down. Just a second. Your wing, your canard and tail both have no CM, only your wing has CM. So let's start with the canard. So mcg equal to, it should have had, if it was not a symmetrical airfoil, there would be an MAC of the canard. In this case it is 0 plus lift on the canard into, what is the distance? Lift on the canard into CG. What is this entire distance? XAC till CG. So what will it be? XCG, yes. So it will be XACC plus XCG. Okay, so this completes the canard. Then we go on to wing. Wing has MACW. So let's start with wing 1. XACW wing 1 plus lift on the wing into the distance. What is the distance? Lift on wing 1 till CG. What is the distance from the leading edge? So this distance, what? Yes, so it is XCG minus XAC wing. This is lift 1, and then you have a drag force plus drag wing 1 into, let's just take this quantity to be ZCG, both up and down. So what will it be? DW1 into ZCG. Then the second wing, is MAC wing 2 plus lift on wing 2 into, it'll be the same same direction, right? Moment will be in the same direction for the wing 2 also. Okay, so it will be XCG minus XAC wing, right? Then drag will be, so drag is in this direction, and about CG it will produce a nose down moment, so it will be negative, right? So you will have minus dW2 ZCG. Now we move on to tail. Tail again is symmetric, so there won't be M. Then you have lift on the tail about CG, again produces nose down. So you have minus lift on the tail into the distances. What is the moment arm? This distance. What is this distance? What is that distance? Yes. So that will be XAC of the tail minus XCG. Any other term? Any other forces that we are leaving out? What we can see here, since both our wings have the same cross section, it's the same airfoil, CL naught, CL alpha, all of them are same, we can cut these terms, right? So this is plus dW1 plus minus dW1, both are same, so we can cut both of those terms. Every other term will be multiplied by 2, so we can write this as LC XACC plus XCGG plus 2 MACW plus 2 LW XCG minus XACW minus LT XAC tail minus XCG. Okay, now let's non-dimensional, because we have two wings here, right? And both of them are the same cross section. They are the same aerodynamic parameters. So instead of writing it separately, I've just taken 2. So LW. Okay. So now let's non-dimensionalize it. That is taking Cm. That is half rho v infinity s square. Okay. So I take Cm Cg. How do we get Cm Cg? I just multiplied this. Okay. So divide it throughout by half rho v square s. And then you get this. So here what will it be? What will it be? You will have a C upon S, yes, and then here you will have, it should have been CL naught plus CL, I'll just write the whole thing first and just for completion, CL alpha of the canard into alpha of the canard into XACC plus XCG. Okay, in our case CL naught is 0 because it's a symmetrical airfoil. So next we take, here what will it be? 2 Cm, yes, yes. Then you have plus 2, what will come here? Again CL naught plus CL alpha of the wing, CL naught of wing into alpha of the wing, and what was the moment arm? XCG minus XACW, then minus, here what will it be? Yes, okay, yes, you are right, correct. There should be one C bar, there should be one C bar, okay. So now the last term will be St upon S, Cl naught of tail plus Cl alpha of tail into alpha of tail, and the moment arm is xac tail minus xcg by c bar. Okay, here ideally there should also be a efficiency factor, that is v infinity dash square by v infinity square, because there's a downwash component associated with the wing that makes the effective velocity at the tail less than the velocity that the wing sees. Okay, so for this derivation we'll just neglect this, but there should be, that term should also be there. Okay, and our CL naught tail again 0 because it's symmetric. Okay, so now let's just write this down completely. CMCG is SC upon S CL alpha C into XACC plus XCG by C bar plus 2 CMAC wing plus 2 CL naught wing. Okay, I'll write that separately. XCG minus XAC wing by C bar plus 2 CL alpha wing XCG minus XAC wing by C bar, and the last term, that is ST upon S CL alpha tail XAC tail minus XCG by C bar. Okay, so now we will split this into Cm naught plus Cm alpha. So your final equation should be, that is Cm is equal to Cm naught plus Cm alpha wing into alpha wing. So all of the terms that depend on alpha wing, we write it separately. All of the terms that are independent, we write it separately. So before that, what is this alpha C? Alpha C. What is the angle of attack seen at the canard in terms of alpha wing? What will it be? So it will be alpha plus the canard setting angle, right? And if the wing had a wing setting angle, this alpha would be alpha wing minus I wing, right? Your effective angle of attack would be alpha wing minus the wing setting angle. But in our case, this wing setting angle is 0. So alpha is equal to alpha wing, but I will just write it alpha wing here. Okay, so your alpha seen at the canard in terms of alpha wing is this. Similarly, alpha seen at the tail is what? Is alpha plus tail setting angle, and there will be a downwash component in this question. Again, that is not mentioned, so we will neglect it. So it is epsilon. Okay, so we will neglect it. And what is epsilon? Epsilon is, again assuming linear variation, epsilon naught plus d epsilon by d alpha into alpha wing. Okay, but in our question it's not given, so we are neglecting it. So now when we substitute all of these terms into this equation CMCG, let me just write it. It will be Cm equal to, okay, this is going to be difficult. SC upon S CLC. I'll write the Cm naught terms first. Okay, Cl alpha C into IC and the momentum, which is, it was the momentum XACC plus XCG what is remaining here? Alpha wing. So that will be SC upon S, CL alpha C, alpha wing, XACC plus XCG. Okay, next will be the wing. What comes for the wing? This is constant, 2 CMAC wing plus 2 CL naught. CL naught of the wing into the momentum. This again will have a C bar. What is it? XCG minus XAC. XCG minus XAC wing by C bar. Then that term is dependent on alpha, I'll put it down. Terms dependent on alpha, I'm putting it down. Okay. So you have CL alpha wing into alpha wing by XCG minus XAC wing by C bar. Then what is left? It's the tail quantity. So you have minus ST upon S CL alpha tail into, what is the term? I tail. And you have XAC tail minus XCG by C bar. And dependent on alpha will be ST by S, CL alpha tail, alpha wing, XAC tail minus XCG by C bar. Okay, so yeah, so now we'll write down the terms that are independent of CM alpha. Okay, dependent on alpha of the wing. Okay, so what is CM alpha? Can you tell me? Can you tell me? I've just written down all the terms below that depend on alpha wing. So just tell me those terms. Just tell me what is CM alpha. CL alpha C. Yes. Yes. Minus ST by S. Yes. Yes. It's not plus. Okay, I didn't write that clearly. This is minus. There's a minus sign here. Minus XCG by C bar. That's it. Is that all? Okay, there is an alpha W here also. Okay, so you have plus CL alpha wing into XCG minus XACW by C bar. Okay, I should have written this on the next page. Is there any way I can copy this? Okay, I'm not sure. Let me I'll just write it down quickly. So CM alpha is SC upon S, CL alpha C, XACC plus XCG by C bar plus ST upon S, CL alpha tail, XAC tail minus XCG by C bar, and you have, okay, this is negative. You have CL alpha wing by XCG minus XAC wing by C bar. Okay, so for neutral point, how do they asked us to find out the neutral point. How do you find out the neutral point from this equation? What is neutral point? Exactly. So you set this to 0, Cm alpha equal to 0, and the Cg location where Cm alpha equal to 0 is the neutral point, right? So what will it be? It will be, yes, so Cm alpha equal to 0. So if I set this as 0 and replace this NP, NP, NP. Okay, so in this equation, let's see what all are our unknowns. Okay, do we know SC? You need to find out SC, you need to find out S, you need to find out ST. Then what else? You need to find out Cl alpha C, Cl alpha, Cl alpha, and Cl alpha tail. What else? XACC, XACW, XAC tail. Yes? Can you tell me how to start? Which one do I start with? Let's do some easy one, which is easy. All of these are unknowns. If you substitute, if you plug in all of these values into this equation, the only unknown will be XNP, right? And then you can find out what XNP is. How do we go about doing this? How do we start? Okay, okay, fine, rearrange the equation, but just start finding these quantities. Okay. Okay, so what do we begin with? We'll start with the aerodynamic parameters first. So you have Cl alpha of the, what was first one? Canard is what? It's 5. But for our equation we need, this is the characteristics of the airfoil. Okay, so when it's written small l, you assume it to be 2D airfoil characteristics. What we need for our configuration is 3D. Yes, so Cl alpha 3D is, what was the relation? Do you remember what the relation was? How do you relate the coefficient of lift of 3D airfoil to 3D wing to 2D airfoil? Okay, the equation was 1 plus L. Yes. So before we begin with the aerodynamic calculations, I believe it's better for us to start with the geometry calculations because these values should be used here. Okay? Okay. So let's try to find out for the canard. We'll start with the canard. Yes. So we'll start with the canard. Okay. Okay. So it says triangular wing. It's not mentioned which. Okay, I forgot to mention which taper axis it is. So let's just take this to be trailing edge. This has no taper, and let's take the wing to be, let me just check where it was. It was the mid chord. Mid chord. Okay, taper axis. Taper axis. So we'll start with the canard. It's tapering about the trailing edge. Root chord is given to you. You need to find out SC, we need the aspect ratio, and we need XAC. Can you calculate this? I'll do it for one, and you guys should do it for the other two cases and give me the value for XNP in the next class. Okay? Will you be able to do that? Yeah, we are running short of, yeah. Yes, yes. Yes. We wrote. Did you understand till here? Till here? Till this equation where I've marked this. Okay, let me just number it. SL. Where is SL? Okay, sorry, that CSC. I'm sorry about that. It's SC. It's the area of the canard. And S is the area of the wing. Okay, I'm sorry about the poor handwriting. So that's SC, that's the area of the canard. S is the area of the wing. And ST is the area of the tail. Um, the other parameters are fine, right? So this is C. And if you take Cm alpha, equate it to 0, you get neutral point. Any other? Yes. Previously. Okay, yeah, sure. You can try this derivation by yourself. I'm sorry. You can just derive it by yourself and let me know if there are any mistakes in this derivation. Okay. So yes, this again is SC. Okay, so I'll do it for the canard. You guys proceed with the tail, and tail is fairly simple. It's a rectangular tail. You guys proceed with the tail and wing and try to find out the neutral point. We'll discuss this once again in the next class, but right now we'll proceed with the canard. So how do you find out SC? SC, area of the tail. It's just a triangle. Half. Okay, the span B of the canard and height was CR of the canard. Okay, let me just go look at the values. B was 1 and CR was 0.5. So it's 1 by 2 into 1 into 0.5. Okay, aspect ratio is BC square by SC, which is, okay, let's calculate these values quickly. Okay, and here it was 1 square by 0.25, which is, okay, okay. Now this is your C bar, and from the leading edge, sorry, if this is your aerodynamic center, we need this value as XAC. We don't need to find out YAC here because we're just taking it in the X direction, okay? XACC was, what will it be? CR. Okay, so this small quantity is C bar by 4 plus what? Plus this remaining part is what? Let me just take another color. So what is this value? How much is that? So 1 in blue is nothing but CR minus C, right? Yes. Okay. So to go ahead with that, we find out C bar. C bar is, what was the equation? 2 by 3 CR 1 plus lambda square 1 plus lambda. In this case, our taper ratio is 0, so it's just 2 by 3 into CR was 0.5. How much is this? It's 0.33. So how much will this be? This will be 0.33 by 4 plus CR was 0.5 minus 0.33, which is plus 0.5 minus 0.33, 0.25, right? Yes. So what have we gotten? We have gotten SCC, we have got XACC, and from that we can find out this value. Let's do that also. Cl alpha C is Cl alpha C 1 plus Cl alpha C by E AR of C. Cl alpha of C was what? 5. Okay. Thank you. That was 5 by 1 plus 5 pi. E was, I think, 0.8 or 0.7. Ratio is 4. So what is this value? And here this is per radians, okay? 3.34. Okay. So this was a mistake that I had seen in the previous course, where this formula, this entire formula is valid only if your CL is in per radians. This has to be in per radians. I didn't mention it explicitly in the question, but this is in per radians. Okay. So we have found out SC, CLAC, Cl alpha of canard, and XACC. Now I want you to do it for these two, for wing and tail, and then find out neutral point. Okay, we'll discuss the final answer in the next session, but do try doing this. Okay. Okay. Do you have any questions? Any other questions? Yes. This one? Yes. What was your question? Okay, okay. So your XAC is this entire distance. Okay, this is your XAC of the canard. So that is what is given here. The red line plus the blue line. So any other questions? I will be uploading this slide in the same location as the previous time, and the recording will also be uploaded on YouTube in the same playlist. So you can go back to that to see the question. Try solving it. We'll meet on Tuesday. Okay. Okay. So if there are no further questions, I think I'll end this here. Okay. Thank you. Thank you. So I'll end it here. We'll meet on Tuesday.